In this video, we are going to cover a foundational result called the nested interval property, which we will see is a consequence of the supremum property. So this follows right out of our third axiom for the real number line. We want to imagine that we have a collection of what are called nested closed bounded intervals. I haven't defined the word closed yet, but they all have this form. So they go from AN to BN, including the endpoints. I didn't write it down explicitly, but AN here is less than or equal to BN, as you would probably expect just from that notation. And then they are nested, which means that the first one from A1 to B1 contains all of the other ones. So notably, it contains the second one, which contains the third one, which contains the fourth one. You can imagine this as, we have the number line R, and then our first interval might look like A1 to B1, just like this. And then the second interval, I2, is, if anything, going to move into the inside. It doesn't have to be strict, but it's usually helpful to imagine kind of coming in like this, A2 to B2. And then the next one could stay right here, meaning A3 could be equal to A2. That's fine. And maybe B3 is like this. Then just could be doing this all day, A4 to B4, etc. Given this setup, that we have this family of intervals of this form where the first one contains the second one, contains a third one, etc., etc., the result is that their intersection is non-empty. So all of these intervals have at least one point in common. Now, you might think that somehow that must happen, that, as we kind of zoom in like this, something is going to survive and live in every single one of these intervals, but we'll see examples where the hypotheses here are necessary. So you can create nested families of sets like this where actually the intersection is empty. I'll show you examples like that in a moment. Let me erase this picture, and when we come back, we will do the proof. Right after I erased my picture, I realized I should talk through the proof on the graphic itself. We need to come up with an element, a real number, that lives in every single one of these intervals. And here's the thought process. What if that element we name X, and we want it to live in every single one of these intervals? What does it look like to live in one of these intervals? It means that you are to the right of the lower side, A sub n for the nth interval, and to the left of the upper side. So let me say this is AN, and this is BN for some choice of index sub n. X has to be greater than or equal to A sub n and less than or equal to B sub n. So I want X to be larger than all of these left sides and smaller than all of these right sides. What does that sound like? X is bigger than these, so it's an upper bound. Sorry, upper bound, that's supposed to say UB, upper bound for the AN. But it's smaller than all of the B sub n. Well, these are also upper bounds for the A sub n. We'll show that explicitly in the proof. So it's like X is an upper bound for these left sides. All the B sub n are upper bounds for the left sides too. And I want to say that I know X to be less than or equal to all of these. That makes it sound like X is an upper bound for these and is perhaps the least upper bound. So that's the proof just done in words and with a terrible diagram. We want to say that the set of left endpoints is bounded above. We'll show that. So it has a least upper bound, a set supremum. We'll call it X. And then we'll say, hey, since X is the supremum, and these are also upper bounds, X has to be less than or equal to these right sides. That puts X in every single one of these intervals and therefore in the intersection. Okay, now I'm going to erase this picture, and everything I just said out loud, we will make rigorous in writing. Now let's translate that visual diagram of how the proof should work into words. So we'll open with proof. We have two collections of points here, the left points and the right points. But as I did in the diagram, we're going to take those left points, collect them into a set, which we will then show is bounded above. So let's let the set capital A be this family of left endpoints. Now what I want to do is show that A must be bounded above. To do that, I have a bit of a trick here. Consider any two indices J and K. Just a vocabulary remark. When we have families like this, where to each natural number we associate a set in this case, I often call those natural numbers indices. So in is an index here. It's indexing us through this collection. So this is a word that we will use sometimes, and it means the natural numbers that we're using to kind of label the items in some collection. In this case, they look like these sets. Because the sets are nested, so here's the trick. I'm going to start with A sub j and say that A sub j is less than or equal to A sub j plus k, because whatever these are, I don't know which one is bigger, I don't care, their sum is bigger. So A sub j plus k, there we go. And then that is a new left endpoint, so it is less than or equal to its corresponding right endpoint for the j plus k interval. So this pairing here forms endpoints for I sub j plus k. And then again, because of the nesting, this is to the left of B sub k. So here I'm saying whatever j is, the left endpoint A sub j is less than or equal to the right endpoint B sub k, whatever k is. In other words, every right endpoint is to the right of all of the left points. Let me pause here just so you can think about that, work back through this inequality on your own, and then we will actually be able to wrap this up very quickly. I just wanted to give you a chance to digest why this is true and what it implies. It implies that each number B sub k from this collection is an upper bound for A, because here this is any such term forming the set A. So each right endpoint B sub k let me say any B sub k, k in the natural numbers, is an upper bound UB for A. Therefore, A is bounded above by the supremum property. A has a least upper bound. So by the supremum property, there exists some real number x, which we can say is the supremum of the set A. We have found an element which will live in the intersection of all of these sets. Why? Because it's an upper bound for all of the A sub n, and it's smaller than all of the B sub n because they are all also upper bounds. Let me write that down explicitly, but at this point we've got an element which will live in this intersection, so we know the intersection will be non-empty. Since x is the sup, let me just continue here. Actually, I'll say since x is an upper bound, x is greater than or equal to A sub n for all indices little n. And since each B sub n is also an upper bound, x is less than or equal to each B sub n because it is the least upper bound. So x is greater than or equal to A sub n, less than or equal to B sub n. That means for each of these intervals, we can put x in the inside. Thus, x is in I sub n for each index n. Being in each set puts you in the intersection. So I can say that since x is in each one of these, it survives the intersection, so the intersection is non-empty. I think it's a really nice, elegant proof. We really just used the supremum property here. I think it's very nice building up just one set to collect the left endpoints, showing all of the right endpoints are an upper bound for that set, and then saying that squeezes the supremum of this set between all of the A sub n and all of the B sub n. I just think it's a really nicely done argument. Let me have you finish copying this down. Then I would like for us to modify the statement a little bit, where we will look at sets which are really moving inward, meaning, you know, it could happen that your family is kind of silly. You could say that for each natural number n, I sub n is the interval from 0 to 1. This satisfies the statement of the hypothesis. So each A sub n is 0, each B sub n is 1. The intersection of all of these sets is 0 to 1 itself, right? So we're going to say, well, what happens if it's a little bit more interesting than that? And we have this idea that our sets are kind of shrinking inwards. Here's a modified form of the nested interval property with an added assumption to capture this idea that in this context, we want to imagine that we have these nested intervals just like we had a moment ago. But this time, I want to insist that they're really being driven inward. To do that, I've added this hypothesis that 0 is the infimum of the set of widths for these intervals. I'm characterizing this inward motion using a set infimum to avoid using words that we haven't defined yet, like limit, what are the widths trending to over time? You may want to say, well, the limit of the widths is 0 or something like that, but I'm trying to stick to only language that we've defined in this course so far. So if you imagine the set of widths, bn minus an, and those widths are like coming inwards to essentially collapse, then that is what we are going to characterize by saying the set infimum here is 0. Then we are still meeting the hypotheses of the original nested interval property, but this time we are going to say that not only does there exist an element in this intersection, but actually it is unique. So the first version of the nested interval property, which is the classic nested interval property, that was all about existence of an element in the intersection. Here, we are focusing on uniqueness. So instead of having that kind of silly example I erased from a moment ago where it was just one interval for all possible n, and we had infinitely many elements contained inside, this time I want to say that if your sets are really being driven inwards, there's just going to be one element that survives the intersecting process. Anytime you are doing a uniqueness proof, it's a good idea to consider contradiction, where you imagine that you have two. So here I want to show there's only one element that lives in this intersection. What if there were two? That almost always leads you to a clean contradiction. That will be our technique of proof. Our proof technique. For the sake of contradiction, suppose that there are two elements, and let me order them. I'll just go ahead and write x is less than y, are both in I sub n equals the interval from an to bn, including the endpoints, for all indices little n. You might already see what has to happen. If x is strictly less than y, because they are distinct, they are not equal, then there's a width just created by the separation that these two elements have from each other. And we are going to be able to drive our intervals inwards to be even smaller than this width, and that's going to set us up a contradiction. It's not a very long argument from here, but if you see where to go with this, see what you can make. So take y minus x, that gives you a positive number. Can you perhaps use a criterion that we've seen already to set up the rest of the argument to reach a contradiction? I will come back in just a moment and finish the proof. What I wanted you to think of was the criterion for a set supremum that we learned previously, but this time recast as a criterion for a set infimum, because here we have that 0 is the infimum of the set of widths. So let's just work through what the criterion should look like for an infimum. Okay, we have that 0 is our set infimum for this set of widths. If you remember, when we looked at the criterion for set supremum, I said if you slide to the left, you're going to pick up an element from the set to the right. So here, the idea is if we slide to the right, there must be something from the set over here. Could be anything between 0 itself and that number. So there must be an interval width somewhere in here. Okay, how much should we slide to the right, though? There is a positive number we could make out of just what's already been written down in this proof. And that positive number is y minus x. Assuming that we have two distinct elements in this intersection, you have the ability to write down an ordering for those two elements, and then that ordering gives you an actual positive number, y minus x. So just for illustration's purpose, let me imagine that there is a width right here. Some member of this set could land right there by our criterion for set infimum. And let's call that member in the proof a sub capital N minus b sub capital, or sorry, going the other way around, b, I'm just trying to write b, okay, b sub capital N minus a sub capital N. So here, my usage of capital N is indicating that it's a specific member of the set. So first the I sub capital Nth interval, these are the endpoints. All right, this width is to the left of y minus x, but y and x must both belong to I sub capital N, so that's going to give us our contradiction there. Let's just write that down. So by the criterion, or let me call it sups and imps, famously stated for suprema, but equally valid for infima. Normally, the criterion is stated for an epsilon, but we don't need to bring in an epsilon here. We have a number in mind that we'd like to work with, which is positive. Given y minus x greater than 0, oh, yeah, that's right. There exists an index capital N such that b sub n minus a sub n is less than y minus x. Excuse me. B sub n minus a sub n is less than y minus x. I didn't exactly state why I'm doing this. Let me just add in parentheses here, as 0 is the infimum of the set. You might want to reword that sentence a little bit. Okay, so from 0, I slid to the right, landing exactly on the number y minus x. By the criterion for sups and imps, there has to be something from the set for which 0 is the infima to the left of y minus x. That gives me this statement. However, x and y are both in I sub n. Therefore, all right, and so the left point a sub n is less than or equal to x, is less than y, is less than or equal to b sub capital N, which means that y minus x is less than or equal to b sub n minus a sub n. Okay, so from y we go up in size to b sub n, from x we go down in size. So this difference is less than or equal to that difference. And that is an exact contradiction of what we just wrote down. What is being contradicted here? Really the existence of this positive number y minus x. So x cannot be less than y. They can't both live in the intersection. We know that something lives in the intersection from the first version of the nested interval property. It must be unique. Thus, I'm going to bring in some notation here that I wouldn't write formally on paper, but it works well on the board. There exists exclamation point. This symbol means unique. So it also means factorial, but in this context, it means unique. So there exists exclamation point is there exists a unique x in this intersection. Okay. I think this proof is really fun too. So I like both the nested interval property proof, that's the classic result, and then also this modification, just saying that if your intervals are essentially collapsing inwards to width 0, then the point that survives the intersection is unique. You're not going to have more than one. We are done with the theory in this lesson, but I would like to work through some pretty fun examples. And for each one, I want you to think about whether or not the hypotheses of either of these statements applied. Let's wrap up with these 6 examples of computing intersections for families of sets which are nested. Let's do this in 2 groups of 3. So go ahead and pause to work through the left side. Then we will go through that together. Pause again to work through the right side. Starting with this first example in the top left corner of your screen, we are looking at nested sets of the form 0 to 1, 0 to a half, 0 to a third, 0 to a fourth, 0 to a fifth, etc., etc. Do these intervals share a point in common? Well, they all have 0. They don't have anything to the left of 0, so no negative numbers, of course. What about to the right of 0? I don't want to write up a rigorous argument, but hopefully what you realize is that thanks to the Archimedean principle, no positive number will survive this intersection. So there's exactly one member of this intersection, and that is the single element 0. This family satisfies that modified form of the nested interval property. So these are nested, closed bounded intervals whose widths are shrinking like the terms 1 over n. For the second one, though, I love this example just because it shows the importance of all of the hypotheses that we had for the nested interval property. You do really need to have intervals that meet the form that we presented. So in particular, I keep using words like closed and perhaps open here. You might want to call these open intervals. The importance here is that the endpoints are not contained in the intervals themselves. So that will be our working understanding of an open interval. Just like before, there's no negative numbers. And again, thanks to the Archimedean principle, there's no positive numbers either. The only candidate is 0, but actually 0 doesn't belong to any of the members of this set. So this intersection is empty. This family does not satisfy the hypotheses of the nested interval property. Okay, her principle, the P word, nested interval proposition. I don't know. Let's move on. What about this one? Here, I just wanted to contrast this example to this one. These are also nested open sets. They don't contain their endpoints. That will be our working understanding again of an open interval. You don't want to see one example and make a conjecture based on that nested families of sets of this form must always be empty. Here we do have something in the intersection. It's 0. Okay, so it's kind of like on a case-by-case basis here. All right. Let's go over to the right side now. Pause if you haven't already done so and work through these 3 examples. This example on the top right should have reminded you of this first example, except for the right side of this family of nested intervals. Instead of going all the way down to 0, we're going down to the number 1. 1 does belong to each of these. Nothing to the right of 1 does, though, because of the Archimedean principle in a very similar way to what we saw here. So this is the interval from 0 to 1, including the endpoints. If you look at this next one, it looks different at first glance. We're dropping 0 on the left. That doesn't belong to any of these. On the right, 1 belongs to all of these sets. Once again, because 1 plus 1 over n will go beyond 1 for every single choice of n that you could make, but nothing to the right of 1. So what I'm trying to emphasize here is that 1 does survive the intersection. We have an interval of this form. Now, this last one often makes students, sorry, I split my lid somehow, makes students a little bit uncomfortable because we're looking here at a family of intervals that looks like 1 to infinity, 2 to infinity, 3 to infinity, 4 to infinity. If you take any finite intersection from that family, it contains infinitely many elements. So if you go all the way out to n equals 50, your intersection would go from like 50 to infinity, and there's infinitely many elements in that. But if you look at this family across all values of n, because of the Archimedean principle, the first version, if I take any positive number x, whoops, sorry, just wrote on top of my example, x, there we go. If x is some positive number, eventually there's a choice of n which is greater than x. So x cannot be in the intersection because it's dropped by that set. Okay, all that to say that this intersection of sets, each of which has infinite length, is actually empty. And sometimes, again, students don't like that when they first see it, but I think once it clicks for you, it's actually a really nice example. Of these, only the first two satisfied the nested interval property. This is just a regular nested interval property. This one had that second version where the width shrunk to 0. For these other ones, I just wanted to show you that like you could have different behaviors if the hypotheses were not satisfied. So here I had an interval, here I had a singleton, I had some empty set examples. So each of the hypotheses in the nested interval principle is important. There's nothing extra there that we don't need. The last remark I want to make is that if I use the words open and closed at any point in this video, I know I did. Do not read too much into that at this moment in time because those words have precise technical definitions that we will learn later. So while you might want to say this is a closed interval, and that is true, and this interval is neither open nor closed because we're missing one endpoint, we have the other, that is true. You may have an understanding of how to use the words open and closed as they apply to intervals. Try not to use them too much at this stage because we are actually going to look at all types of open and closed sets, and we want to make sure that we really learn the definitions that we will see in quite a bit. Okay, so I'll wrap this up here. Thank you for your attention.